In this video, we'll talk about cumulative distribution functions, or CDFs. In particular, we'll look at CDFs for continuous random variables in this video and discrete random variables in the next. Consider an example. Suppose you're going to the bus stop and let x be the waiting time in minutes until the bus arrives. Further, suppose that x is uniformly distributed from 0 to 10. That is, you're equally likely to wait any time between 0 and 10 minutes. A formula and plot of the uniform PDF are shown here. Now, suppose you want to know the probability that you won't have to wait any longer than 1 minute. The probability of this event is represented by the shaded region below. We could calculate this probability by the area of the shaded rectangle, but let's formalize things. The probability that waiting time x is less than or equal to 1 minute can be calculated by integrating the PDF from 0 to 1. Going through the steps, we calculate that there's a 0.1 probability, or 10% chance, that your wait time won't exceed 1 minute. Similarly, the probability that you won't have to wait longer than 2 minutes is 0.2. We can perform similar calculations for any possible waiting time. For example, there's an 80% chance that you won't have to wait longer than 8 minutes, and a 100% chance that you won't have to wait longer than 10 minutes. Notice here that each time we increase the possible waiting time, we accumulate more density in these shaded regions. In general, for any specific waiting time t between 0 and 10 minutes, the probability that you won't have to wait longer than t minutes is 0.1 times t. We calculate this value by integrating the uniform PDF of 0.1 from 0 up to t. The calculations we've done here are connected to the cumulative distribution function, or CDF. The CDF of a random variable x captures the rate at which x accumulates either density when x is continuous or mass when x is discrete. I emphasized accumulates here in order to connect the terminology of cumulative distribution function with the concept. Mathematically, the CDF is denoted by a capital letter F, and by definition, for a given value of t, f of t is equal to the probability that x is less than or equal to t. Further, we can plug in any t value here. CDFs are defined for values of t on the entire real line. Before moving on, note that as is convention, we're using t as the input label for the CDF. This is no different than using x. We just have to be mindful of the notation we're using and be consistent with that within our calculations. And this might seem like a pointless and confusing switch here, but we'll see at the end of this video that the use of t instead of x helps avoid confusion when we're actually calculating or building the CDF. Now let's construct the CDF of our uniform waiting times. Thus far, we've defined the CDF for just a segment along the real line. To define the entire CDF across the entire real line, we have to consider 3 situations: negative waiting times, waiting times on the support of x between 0 and 10, and waiting times that are as big or bigger than 10. We actually already defined the CDF across the second scenario. When waiting time t is within the support from 0 to 10, the probability of waiting t or less minutes is 0.1 times t. That is, the CDF at t is 0.1 t. Next, consider negative wait times. For example, what's the CDF at -1? That is, what's the probability that our wait time ends up being less than or equal to -1? Well, logically, it doesn't make sense that a waiting time could be negative. And mathematically, it's also true that there's a 0 probability of waiting -1 minute or less. The PDF is non-existent or 0 in this range. Thus, the area below it is also 0. In general, for any negative waiting time t, there's a 0% chance that you'd wait under t minutes. Thus the CDF f of t equals 0 in this entire range. Finally, consider wait times at or above 10, the maximum waiting time in our model. For example, what's the probability that you won't have to wait more than 11 minutes? That is, that you wait 11 minutes or less. Well, since we know that your wait time has to be between 0 and 10 minutes, there's a 100% chance that your wait time will be under 11 minutes. The entire model falls below 11. In general, for any wait time t at or above the maximum of 10 minutes, there's a 100% chance that your wait time will be under t minutes. Thus, f of t equals 1 across this entire range. Okay, let's put this all together. We started with a uniform model of your waiting time. We then built a CDF which we can use to calculate the probability that your wait time won't exceed t minutes. Combining the three scenarios where t is below the support, where t is within the support, and t is above the support, the formula for this CDF is shown here. Next, let's plot the CDF. And we'll pick this apart. First, below our support, the CDF, like the PDF, is flat at 0. We haven't accumulated any density yet. Once we get in the range of support from 0 to 10, the CDF starts climbing as we accumulate more and more density. For example, there's a 0.2 probability that your wait time is at or below 2 minutes. There's a greater 0.5 probability that your wait time is at or below 5 minutes. And an even greater 0.8 probability that your wait time is at or below 8 minutes. Notice that our climb here has been very steady or linear. This is due to the uniform nature of waiting times. The density does not accumulate faster in one region of the support than another. Finally, the CDF flattens out and stays at 1 once we get to wait times t at or above 10 minutes, that is, above our support. At this point, we've accumulated all possible density and can't accumulate any more. Stepping back from our example, the CDF for any continuous random variable x, f of xt, is defined as the probability that x is less than or equal to t. When x is continuous, we can calculate this probability by integrating the PDF, little f of x, from negative infinity to t. This formula also indicates the importance of using t as the label for our CDF input. If we used x, which might feel more natural, we'd be using x to represent two different concepts: the variable that we're integrating and the limits of this integration, and we can't do that. Finally, those CDFs of other continuous random variables will look different than the one we built in our waiting time example. They all share the same properties. First, the output of a CDF will always be between 0 and 1. After all, the CDF is a probability. Second, the CDF will always be continuous and non-decreasing. That is, a CDF might be flat in spots, but it can never go down. Finally, it will always approach the limits of 0 and 1. Specifically, as t goes to negative infinity, the CDF will approach 0. And as t goes to positive infinity, the CDF will approach 1. Finally, you might be wondering why we care. Well, CDFs are more than just a random feature of a model. First, like a PDF, CDFs are unique to a model. Thus, they are an important tool for defining and identifying models. Unlike a PDF, which doesn't have any contextual interpretation, the CDF of a continuous random variable x has a nice interpretation as a probability. And though we won't get into the details here, the CDF is needed for many statistical applications and data analysis tools, including things like survival analysis, finite population sampling, and Kolmogorov-Smirnov tests.